If you take a standard, perfectly drawn heart icon and you just drop it right into a user interface, 99% of UI designers working today will assume it means one of two things.
Right, either like or add to favorites.
Exactly. It's one of the most ingrained digital reflexes we have. But recently, this development team built a localized agricultural app specifically for farmers.
Okay.
And they placed that exact same ubiquitous heart icon next to a list of crops and livestock. So when they ran usability tests, a massive 67% of the farmers thought the heart meant the product is healthy.
Oh, wow.
Yeah, only 21% actually understood it as a digital bookmarking tool. And just like that, because of one tiny miscalculated geometric shape, the core navigation of the whole application just completely collapsed.
That is wild, but it really highlights the problem, doesn't it?
It really does. So, welcome to the deep dive. Today, we are tearing down the smallest, most underestimated, and I mean arguably the most powerful elements on your digital screen. We are dissecting Chapter 13, which is simply titled Icons, from the incredibly comprehensive book Design User Interface.
It's such a vital chapter.
It really is. If you are building a career in design or engineering or product management, this is your masterclass in the invisible visual vocabulary that literally controls user behavior. Okay, let's unpack this.
To truly grasp the gravity of that farmer anecdote you just shared, we really have to reevaluate how we perceive the digital canvas. Because icons are, they're rarely treated with the respect they command.
Yeah, we just treat them like decorations.
Exactly. We view them as aesthetic garnishes.
Right.
Just the finishing touches applied right before a product ships.
Yeah.
But structurally, there are the fundamental load-bearing pillars of a user's journey.
Right.
If you think about an interface as a physical environment, the icons are the exit signs, they're the door handles, the light switches.
That's a great analogy.
Yeah, and when that visual vocabulary fails to map accurately to the user's mental model, like it did with the agricultural app, the entire beautifully coded architecture behind the screen is rendered inaccessible. The stakes are incredibly high.
And I feel like that completely shatters this assumption that the entire tech industry suffers from, which is this myth of universal meaning.
Oh, absolutely.
Because we've taken the three-dimensional world, flattened it out, and simplified it into these minimalist vector paths, we just assume we've created a universal human language.
Right, which we clearly haven't.
But wait, let me push back on this for a second. Cognitive friction isn't always a fatal error, right? I mean, even if the farmers initially thought the heart meant healthy livestock, wouldn't they just tap it, realize it saved the item to a list, and then simply, learn the new behavior?
You'd think so, yeah.
Like, we all had to learn what a hamburger menu was at some point. Is the learning curve really that dangerous?
What's fascinating here is the assumption that the user will actually grant you the grace period to learn your specific interface. In modern digital ecosystems, user patience is measured in milliseconds.
Yeah.
Yes, humans are incredibly adaptable. We can learn that a star means favorite, a ribbon means save, and a heart means like.
Sure.
But every single time you force a user to guess, to tap an icon just to see what it does, you are taxing their cognitive load. And in domain-specific software, like an agricultural management tool or medical software or aviation dashboards.
High-stakes environments.
Exactly. The user is already operating in a high-stress, deeply contextualized cognitive framework. We can call it farm mode or surgery mode.
Wow, farm mode, I like that.
Right. And when they are in that mode, their professional context just completely overwrites generic consumer tech assumptions. A farmer's entire livelihood is predicated on the health and vitality of living organisms.
Right, so to them, a heart literally means a heartbeat.
Semiotically, yes. A heart signifies a beating pulse, vitality, health. To force them to abandon their deep-rooted professional context just to learn your arbitrary digital shorthand, well, it's a failure of empathy on the designer's part.
That makes perfect sense. It's semiotics, right? We are assuming the signifier, the heart shape, always points to the same signified concept of saving an item.
Precisely.
But the target audience brings their own dictionary to the app. So if the geometry itself is mathematically pristine but semiotically flawed, how do we bulletproof our interfaces? I mean, we can't interview every single user to find out what a square means to them.
No, you definitely can't do that.
Which brings us right to the great debate in UI design, the absolute necessity of text labels.
It is the ultimate safety net, and honestly, it shouldn't even be a debate anymore.
Really?
Yeah, the golden rule established in Chapter 13 is unequivocal. An icon accompanied by a text label dramatically reduces cognitive processing time and practically guarantees immediate understanding.
But designers hate labels.
They do. Designers often resist labels because icons are, visually pleasing. They establish the aesthetic tone of a product, they create a sense of minimalism, and crucially, they save highly valuable screen real estate.
Right, pixels are expensive.
Exactly. But we have to ruthlessly prioritize function over form. An interface must be clear before it is beautiful. And a label provides that irrefutable clarity.
But introducing text introduces its own set of physics, right? Because if my icon is a tiny little shopping cart and my label underneath it is view selected items for purchase, I've completely destroyed the spatial efficiency of the navigation bar.
Oh yeah, completely ruined it.
So I'm imagining there is a strict constraint on how we deploy these text labels.
Absolutely. The constraint is processing speed, which directly correlates to word count. The ideal label is one word, maximum two.
It's one word.
Just one is possible. The underlying psychology here relies on Hick's law and pattern recognition. We don't actually read familiar short words letter by letter.
Wait, we don't?
No, our brains process the entire silhouette of a short word, almost as if it were a shape itself. So if you pair a cart icon with the word cart, the brain synthesizes the visual symbol and the text symbol simultaneously. It confirms the action in a fraction of a second.
That's amazing.
But if you use a long, complex phrase, the user has to switch from visual processing mode into reading comprehension mode. You want recognition, not reading.
That distinction between recognition and reading is brilliant. But let's look at the exceptions, because the text does offer us a bit of a free pass for a very specific subset of icons.
It does, yes.
If we are designing for a broad audience, there are certain shapes that have achieved such absolute ubiquity over the last 2 decades that they've essentially become like digital oxygen. We don't need to label them because the collective learning curve has already been surpassed globally.
Yeah, those are the universal icons.
Right.
While you must always consider your specific context, these are the shapes that have saturated the market so thoroughly that you can generally safely deploy them without a text label to save space. The source specifically identifies several key players here.
Let's list them out, because for anyone listening who is, auditing their own app right now, these are your safe zones. First is the add to favorites icon, which is generally universally recognized as a star or a heart. Assuming, again, you aren't building a tool for cardiologists or farmers.
Right. Got to remember the context.
Then we have the map pin for location data, the menu icon, specifically the 3 horizontal lines known as the hamburger menu, the circular arrow for refresh or reload.
Classic.
Yep. The physical camera lens for open camera, the trash can or the X for remove or delete, the trusty magnifying glass for search, and the left pointing arrow for back.
Now, however, even within that heavily established universal list, we have to apply a critical layer of demographic empathy.
Oh, interesting. Like what?
The text provides a vital caveat regarding top-level navigation. Let's take the hamburger menu or the back arrow. If you are designing a product where a significant portion of your target audience skews older, or perhaps possesses a lower baseline of digital literacy, the recommendation shifts immediately.
How so?
You keep the text labels.
Really? Even for the hamburger menu? I feel like that's been standard since, the early days of smartphones.
Well, we assume it's standard because we live in this ecosystem.
Yeah.
But abstract symbols, like 3 stacked horizontal lines, do not possess any inherent physical equivalent.
That's true.
A trash can looks like a physical trash can. A magnifying glass looks like a magnifying glass. But 3 lines do not look like a hidden off-canvas navigation drawer.
Ah, no, they really don't.
It is a purely learned symbol. For an older demographic, that learning might not be hardwired. So underneath those 3 lines, you simply write menu. You never let a desire for a minimalist, uncluttered aesthetic compromise the fundamental usability of the product for the people who actually need to navigate it.
Okay, so if we've committed to using a label, it naturally raises a question about the icon itself. If I have the word home written out, providing total clarity, does that mean I'm free to make the accompanying house icon incredibly intricate and detailed?
No.
Because the text is there to do the heavy lifting, can the icon just become pure, complex art?
It's a logical assumption, but the text explicitly warns against this. There is a strict inverse relationship between visual complexity and cognitive comprehension speed.
Okay, break that down for me.
Even with a label, if an icon possesses too many vector paths, excessive line work, or tiny decorative elements, the human visual cortex still attempts to decode the entire image before moving on.
So it slows you down.
Exactly. It acts as a visual speed bump. Simplicity isn't merely a trending design aesthetic, it is a hardline functional requirement. You must distill the object down to its absolute bare minimum geometric essence.
Which brings us directly into the engineering room. We know when to use them, we know why we need labels, and we understand the semiotic pitfalls.
Now let's talk about digital anatomy. Let's look at what these things are actually made of.
This is where it gets really practical.
Yeah. For a junior designer, the immediate instinct is to open Figma or Illustrator, grab the pen tool, and just start freehanding vector points to draw a shape.
I see it all the time. But Chapter 13 completely demystifies this approach, arguing that building icons is much closer to architecture than it is to painting.
It is entirely architectural.
Yeah.
The core philosophy here is that almost every successful, highly legible icon is constructed by combining the most basic geometric primitives.
Like what?
Perfect squares, perfect circles, and perfect triangles. Now, it is true that we live in an era of massive, high-quality, open-source icon libraries. You can download a perfectly functional icon set in seconds. But the text strongly advocates that anyone learning user interface design must physically draw these shapes themselves from scratch using geometric Boolean operations.
Why though? I mean, if a perfectly optimized, mathematically sound magnifying glass icon already exists for free online, aren't we just reinventing the wheel by drawing it from scratch?
Because if you don't understand how the engine works, you can never tune the car.
Oh, that's a good point.
By utilizing Boolean operations, adding a circle to a rectangle, subtracting a triangle from a square, you learn the foundational grid mechanics of digital shapes.
Right.
When you eventually download an icon pack, it will rarely match the exact distinct visual branding of your specific product. You will need to modify stroke widths, adjust corner radii, and tweak proportions.
And if you don't know how they were built.
Exactly. If you've never engineered an icon from primitive shapes, your modifications will likely destroy the mathematical harmony of the original file. You have to learn how to build before you can effectively dissect and rebuild.
Let's break down that magnifying glass example because it perfectly illustrates this concept of architectural distillation. When you look at a search icon in a final app, it feels like a unified, complex object.
Sure does.
But if you deconstruct its vector data, it is astonishingly primitive. It is nothing more than an empty geometric oval intersecting with a short, straight, rectangular line.
A circle and a stick.
A circle and a stick. That's the entire anatomy of one of the most used digital tools on Earth.
And understanding that anatomy leads us to one of the most critical yet frequently violated technical rules in icon design.
Okay, lay it on me.
Let's say you are tasked with drawing that magnifying glass. The handle sits at a 45-degree angle. The immediate instinct for an untrained designer is to select the line tool and attempt to draw a diagonal line.
Natural.
Or if they need an X for a close button, they try to draw two intersecting diagonal lines.
Right. You see a tilted object, so you try to draw a tilted object. And the result is always a nightmare.
Completely.
The vector points don't snap to the pixel grid correctly, the edges look blurry, and getting the exact length and symmetry feels impossible. Here's where it gets really interesting, because the text reveals this foundational pro tip that completely blew my mind the first time I learned it. It's the rotation hack.
It is brilliant. The rule is remarkably simple, but profoundly effective. You must never draw an icon at an angle.
Never.
Never. Every single element should be constructed perfectly straight, aligned strictly to the vertical and horizontal axes of the pixel grid.
Okay, so how do I make an X?
If you need a plus sign, you do not draw it as a unified shape. You draw one perfect vertical rectangle, ensuring its edges align exactly with the pixel grid. Then you draw one perfect horizontal rectangle. You align them perfectly on their centers.
Okay, I have a perfect plus sign.
Right. And if your goal is to create an X, you do not start over. You take that flawlessly engineered orthogonal plus sign, you merge the two rectangles into a single Boolean shape, and then you rotate the entire final object 45 degrees.
It's mathematically bulletproof. The text uses the pencil icon as another great example. A classic edit icon is usually a pencil tilted at a jaunty angle.
Yeah, usually pointing down and to the left.
If you try to draw a tilted pencil, getting the triangle of the tip to perfectly align with the rectangle of the body while everything is off-axis is, well, it's an exercise in frustration.
Oh, it's impossible to get pixel perfect.
Instead, you build the pencil pointing straight up, a vertical rectangle for the body, a vertical triangle for the tip, a small vertical square for the eraser. You align them all flawlessly on a straight center line, merge the paths, and then you apply the tilt. You are essentially manufacturing the raw materials in a controlled, flat environment and posing the final product only after construction is complete.
Exactly. And while you are in this construction phase, the text emphasizes another non-negotiable technical methodology,
Which is?
utilizing strokes rather than fills for the initial build. Constructing your icons using vector strokes, which are the mathematical outlines of the paths, rather than filling the shapes with solid color blocks, grants the designer immense downstream flexibility.
Flexibility how?
Well, by keeping the shapes as strokes, you can globally adjust the thickness, the visual weight of an entire icon set with a single numerical tweak.
Oh, that saves so much time.
It is essential when you need to match the density of your icons to a newly chosen typeface, or when an interface transitions from a light mode to a dark mode and requires a subtle adjustment in visual mass to maintain legibility.
Okay, so we've mastered the geometry, we've built our primitive shapes, we've snapped everything perfectly to the grid, we've used our rotation hacks, and we have a technically flawless framework.
Sounds good.
But technically flawless geometry can still feel incredibly sterile, right? A perfectly mathematical circle and stick might work for a database management tool, but it might feel terrifyingly clinical in a children's educational app.
Very true.
We have to inject emotion into the math. Let's dive into the psychology of style. How do we dial up friendly versus serious?
Well, before we can adjust the emotional dials, we must address the foundational requirement of all styling.
Which is?
Absolute consistency.
Yeah.
The text is utterly uncompromising here. Every single icon within a user interface must look as though it was forged by the same hand using the exact same set of physical tools.
Right.
If a user navigates from a settings menu using one style of iconography to a dashboard using a downloaded set with slightly different proportions, the brain registers that discrepancy immediately.
It just feels off.
Even if the user can't articulate why, the interface will feel fractured, chaotic, and subliminally, it degrades the perceived trustworthiness and professionalism of the entire application.
So assuming we commit to a unified design language, what are our primary levers for emotional manipulation? The text isolates two major structural factors: roundness and sharpness. Let's tackle roundness first. How does the radius of a corner change the psychological perception of a digital shape?
It traces back to our physical evolution and our interaction with the material world. Roundness inherently equates to safety and approachability.
Like baby-proofing a house.
Exactly. Think about industrial design. We do not manufacture toys for toddlers with razor-sharp 90-degree titanium corners. We soften the edges. We make them physically safe to handle.
Right.
The human visual system processes digital representations identically. Rounded corners and softened line terminals communicate a friendly, consumer-facing, relaxed environment.
Okay, that makes sense.
And the text provides a fascinating caveat, specifically for outline icons.
Oh.
If you want a stroke-based icon to truly feel friendly, a thin line won't work, even if the corners are rounded. A very thin, rounded line can still feel delicate, fragile, or overly clinical.
So how do you fix it?
To achieve a genuinely friendly aesthetic, you must pair those rounded corners with a thicker, more robust stroke weight. It gives the shape a sense of sturdiness and approachability.
And on the opposite end of the spectrum, we have sharpness, the serious, uncompromising factor.
Precisely. Sharp 90-degree corners, or corners with an almost imperceptibly small radius, communicate exactness, precision, and formality. They feel engineered rather than sculpted.
Ah, okay.
When you pair sharp corners with a minimalist geometric structure and a very thin stroke weight, you project an aura of extreme professionalism. This is exactly the visual language you expect and subconsciously demand from enterprise analytics dashboards, banking software, or cybersecurity applications.
Yeah, I definitely want my banking app to look engineered.
Right. A thick, bubbly, rounded icon in a financial portfolio interface would subtly undermine the user's confidence in the accuracy of the data. The geometry must reflect the gravity of the task.
That makes so much sense. It's like wearing a tailored suit versus a comfortable hoodie. They both cover your body, but they communicate entirely different intentions.
Great analogy.
Now, there is another massive rule regarding style consistency in the text, and it revolves around the core rendering method, the fill versus outline rules. The source states emphatically that you should never mix outline icons and filled icons within the same static navigation structure.
Ever.
If my home icon is just an outline of a house, my settings icon next to it cannot be a solid, filled-in black gear. You have to pick a lane and stay in it.
If we connect this to the bigger picture of cognitive processing, mixing those two rendering styles indiscriminately completely destroys the visual hierarchy of the interface.
Because of the weight.
Yes. Filled icons possess a significantly heavier visual mass than outline icons. If you mix them arbitrarily, the filled icons will dominate the user's attention, creating an unbalanced, chaotic focal point.
Okay, but is there any exception?
However, the text details the one absolute vital exception to this rule, which is state changes.
Right, using the switch in style as a communication tool itself.
Exactly. You are permitted and often encouraged to mix outline and filled icons if you're strictly using the transition to indicate a change in status. The classic example is the like or favorite interaction.
Back to the heart icon.
Exactly. The icon sits in its default inactive state as a hollow outlined heart. When the user taps it, triggering the action, the icon instantly transforms into a solid filled heart.
That's super satisfying.
It is. In this highly specific context, the sudden introduction of visual mass provides immediate, satisfying feedback that the system has registered the input and the state has changed.
But as a baseline aesthetic choice across a static toolbar,
It is forbidden. Consistent edge radii, consistent stroke weights, consistent fill types. This mathematical discipline is how a designer builds a foundation of subliminal trust with the user.
Okay, so picture this. You've meticulously engineered an entire suite of icons. The geometry is flawless, snapped to the grid. The emotional tone is perfectly calibrated. A beautiful set of friendly, rounded outline icons with a satisfyingly thick stroke.
Sounds lovely.
They look absolutely incredible, museum quality, blown up on your massive 32-inch 4K Retina display. Every single Bezier curve is a work of art. But we don't design for ideal conditions. We design for the messy real world. And the real world means that your masterpiece is going to be ruthlessly scaled down to a tiny 16 by 16 pixel square, rendered on a cheap 5-year-old smartphone screen with a cracked glass overlay.
The harsh reality.
What happens to our perfect geometry then? We have to examine the scaling survival matrix. Let's talk about legibility and the level of detail under extreme physical stress.
This transition from the idealized canvas to the physical constraints of user hardware is where many junior designs completely disintegrate.
Why is that?
Chapter 13 establishes a fundamental, almost physical law for digital displays, the rule of detail. It states that the smaller the intended display size of an icon, the less detailed its internal geometry must be.
Because it just gets messy.
Exactly. The reasoning is rooted in the physical limitations of pixel density. As a complex shape shrinks, the negative space between its vector paths vanishes. Intricate lines crash into one another, blending into an illegible, muddy cluster of pixels.
You just lose the fidelity entirely.
You can, of course, inject more detail into icons designed exclusively for large desktop displays, but you must always weigh the cognitive cost. Complexity slows down recognition.
I always visualize this concept like trying to read a densely printed, thick textbook from all the way across a dimly lit room. You know it's text, but your eye physically cannot resolve the negative space between the letters. The paragraphs just become solid, gray, rectangular smudges on the page.
That's exactly what happens.
The exact same optical failure occurs when complex icons shrink. To really understand this, the text breaks icon, rendering down into 4 specific matrix combinations, showing us exactly what survives the scaling process and what gets destroyed. Let's analyze these deeply.
Sure. The first quadrant of the matrix is the combination of simple and filled. This means primitive geometry, rendered as a solid block of color, often with slightly softened corners.
And how does that scale?
The text champions this as the gold standard for universal legibility. Because this style relies entirely on recognizing the overall mass and external silhouette of the object, rather than deciphering fine internal line work, it survives aggressive downscaling beautifully. A solid, simple shape retains its visual integrity whether it is 100 pixels wide or 12 pixels wide.
That makes sense. It's like a shadow puppet. As long as the outline is clear, you know what animal it is.
Exactly.
Okay, so the second combination is simple and outlined. So we have our primitive geometry, but no internal fill, just the stroke path.
This combination generally performs very well across most standard sizes, but it comes with a critical, non-negotiable condition.
Which is?
The stroke must be remarkably thick. If the lines possess enough physical weight, the simple structure will scale down effectively. However, the text issues a strong warning here.
Oh, about what?
Because it relies on lines rather than solid mass, it will inherently lose some fidelity at microscopic sizes. Therefore, if you commit to this style, it is imperative that you rigorously test your designs on physical devices at the absolute smallest intended display size to guarantee the shape remains recognizable.
So always test on an actual phone. Now we cross over into the danger zones, quadrant 3. complex and filled.
Right. When you utilize solid fills but introduce a high frequency of sharp corners, jagged edges, and intricate cutouts, imagine a tiny, filled-in icon of a Gothic cathedral with dozens of tiny spires.
That sounds like a nightmare to scale.
The text notes a rapid degradation in legibility during scaling. As the available pixel grid shrinks, the sharp, minute details physically bleed into the filled negative spaces. The distinct architectural features are swallowed by the mass, and your beautifully detailed cathedral rapidly devolves into an unrecognizable, muddy blob.
Which leaves us with the final quadrant, combination 4, which the text essentially paints as an absolute nightmare scenario for small screens. Complex and outlined.
This is unequivocally the most problematic approach for responsive design. When you take highly detailed, intricate geometry and render it using very thin outline strokes, you are setting yourself up for catastrophic failure at small scales. And the text pinpoints the exact technological culprit responsible for this destruction.
Wait, there's a specific technology doing this?
Yes, anti-aliasing algorithms.
Let's pause and really break that down, because I think a lot of people use the term anti-aliasing without actually knowing what the computer's doing. Why does the screen intentionally destroy our thin lines?
It's an attempt to solve a physical limitation. Digital screens are made of a rigid, square grid of physical pixels. When you try to draw a perfectly smooth curved line, or diagonal line, across a grid of squares, it is physically impossible.
Because it's all little blocks.
Right. The raw result is a jagged stair-step pattern. This is called aliasing. To make the line appear smooth to the human eye, the rendering engine uses anti-aliasing. It calculates the geometric path of the curve and adds semi-transparent, lighter-colored pixels along the jagged edges to create an optical illusion of smoothness.
Okay, so it's basically blurring the harsh edges to trick our brains. That sounds helpful, honestly.
It is incredibly helpful for typography and large graphics. But here is the fatal flaw for icons. When a line is only 1 pixel thick and the overall icon is scaled down to a tiny size, the anti-aliasing algorithm is forced to apply that semi-transparent blur to the entire line just to render it on the reduced grid.
Oh no.
The mathematical blur completely overpowers the solid color of the stroke. The lines literally fade away. They become a faint, ghostly, blurry mess.
What?
On lower resolution displays, a complex outlined icon might practically disappear entirely. The design isn't just hard to read. It is actively obliterated by the screen technology trying to render it.
That is a phenomenal technical insight. It reminds us that we aren't just designing theoretical concepts on an idealized infinite canvas. We're engaged in a constant physical battle with the hardware limitations of the user's screen.
Absolutely.
Which actually brings us to the final and, frankly, I think the most advanced, mind-bending concept for beginners in this entire chapter. We've managed to survive the scaling matrix. Now we face the ultimate optical illusion. Section 6 is all about icon size and the bounding box.
This is the precise moment where UI design transcends pure logical geometry and enters the highly subjective, nuanced realm of optical perception.
I love this part.
The fundamental problem designers face is this. You can build a set of icons that share the exact same stylistic rules, the exact same stroke weight, and are drawn to the exact same mathematical pixel dimensions. Let's say they were all strictly contained within a 24 by 24 pixel square. The math dictates they are identical in size.
Sure.
Yet when you place them side by side in a navigation bar, the human eye will violently disagree. They will not look the same size.
Yes. This is the square versus oval illusion, and it completely shifts how you have to think about design software. The source uses this incredibly simple, irrefutable example. If you open Figma right now, and you draw a perfect square that is exactly 100 pixels wide and 100 pixels tall.
Okay.
Then right next to it, you draw a perfect circle that is also exactly 100 pixels wide and 100 pixels tall. If you look at the properties panel, the software swears to you that both objects are 100 by 100. The math is identical. But when you look at them on the canvas, the square will look significantly more massive. It looks heavier, dominant, almost like it's bullying the circle.
And the explanation for this is the concept of optical weight or visual mass. The geometry dictates the perception. A square looks bigger because its geometry pushes entirely into the 4 corners of its bounding box. It utilizes every available pixel of area within that 100 by 100 grid.
And the circle.
A circle, by its very definition, curves inward, actively abandoning massive amounts of pixel area in those 4 corners. Mathematically, a 100 by 100 circle physically contains about 21% less area than a 100 by 100 square. The square literally takes up more physical light on the screen, making its visual mass feel significantly heavier.
So why is this optical discrepancy so dangerous? I mean, if the square looks a little bigger, does it really ruin the app?
It creates a fatal imbalance in visual hierarchy. As Chapter 13 explicitly states, all icons utilized in the same context, like a bottom navigation bar, must be proportionally scaled to carry the exact same visual weight.
Okay.
If you have a solid square-ish calendar icon sitting next to a circular user profile icon, and they are mathematically the same dimensions, the visually heavier calendar icon will unfairly draw the user's eye.
It's distracting.
It acts as a visual magnet, dominating the space and entirely breaking the harmonious flow of the interface. It feels unbalanced, like a painting hung crookedly on a wall.
Yeah, that's annoying.
The core lesson here is that you cannot simply type 24 by 24 pixels into the width and height boxes, align your elements, and assume the job is done. The software's math is actively lying to human perception. You must adjust the shapes manually so they appear equal, regardless of what the numbers say.
Okay, but how? If I can't trust the explicit numbers in the software, what framework do I trust? If I'm just guessing, won't I just create a different kind of mess? This brings us to the precise, highly systematic methodology outlined in the text, the bounding box solution.
This is how professional designers manage optical weight across massive, complex design systems. Step 1 is establishing your anchor. You almost always start with a square, or a highly blocky icon. Because the square has the maximum visual mass, it becomes the baseline.
Makes sense.
You draw a square, let's say 20 by 20 pixels, within a 24 by 24 pixel artboard. That 20 by 20 area becomes what the text refers to as the safe area, or the bounding box. It is the visual standard, the physical volume that every single subsequent icon must measure up to.
Right, so the square sits perfectly inside the safe area. It is the heavy anchor. Now, what happens when I need to introduce a circular icon, like a magnifying glass or a globe, into this system?
You recall that the circle naturally loses 21% of its mass in the corners. Therefore, to make the circular icon look as visually heavy as your anchor square, you must physically draw the circle slightly larger than the square bounding box. You intentionally force the edges of the circle to overshoot the safe area lines to compensate for the lost corner space.
That concept is directly stolen from typography, isn't it?
Yes, it is.
When you look at a beautifully set typeface, the round letters like O and C actually drop slightly below the baseline and rise slightly above the cap height of the flat letters like H or E. If they were mathematically flush, the round letters would look tiny. Iconography is using the exact same optical trick.
It's the exact same principle.
Okay, what about triangles? What if I'm drawing a play button?
Triangles suffer from an even more extreme loss of visual mass than circles. A triangle is mostly negative space converging to a single point. To compensate for this severe lack of density, a triangle must be scaled up significantly, often pushing well outside the theoretical bounding box, so that its overall spread of pixels begins to match the dense, solid block of the anchor square.
And the rules get even more specific as the geometry shifts. What if my icon is naturally wide and horizontal, like a rectangular keyboard icon or a credit card?
Wide horizontal geometries inherently lack height, which means they lack overall vertical mass. To compensate for their squat nature, they cannot simply touch the left and right edges of the safe area. They must be stretched even wider, extending significantly past the vertical boundaries of the bounding box to acquire enough visual presence to stand next to the square.
And conversely, if I have a tall, narrow, vertical icon, like a classic microphone or mobile phone symbol,
You apply the exact inverse logic. Because the object severely lacks horizontal width, it must be scaled to be much taller than the square bounding box. You stretch it vertically past the horizontal safe lines until its height compensates for its lack of girth.
And then there are the wild cards, the irregular shapes. What if I'm designing an icon that represents a leaping dog or a stylized flame? There is no clean mathematical geometric equivalent.
The text openly acknowledges that irregular shapes are the ultimate test of a designer's skill. There is no simple, programmatic geometric rule you can apply to a leaping dog.
So what do you do?
The methodology here relies entirely on trained optical perception. You must place your irregular icon directly side by side with your solid anchor square. Then you step back, you squint your eyes to blur out the details and focus purely on the silhouettes, and you manually scale the irregular shape up or down.
Wow, just by eye.
You adjust it pixel by fractional pixel until the dark, blurry mass of the dog feels exactly as heavy as the dark, blurry mass of the square.
You literally have to blur your vision to see clearly. That is incredible.
This raises an incredibly important question for the industry. how do we train junior designers to actually see optical weight? We spend so much time teaching them the software, teaching them the exact mathematics of grids, padding, and flexbox layouts.
Yeah, we're obsessed with the numbers.
But creating truly exceptional, invisible interfaces requires a fundamental, terrifying shift. You have to transition from being a rigid technician who blindly obeys numerical inputs to an artist who deeply trusts human optical perception over the machine's mathematics.
It really does. You have to learn to squint at your screen and feel the balance in your gut, rather than just neurotically checking the pixel readouts in the properties panel. It's a completely different cognitive muscle, and it's what separates good digital products from truly great ones.
I couldn't agree more.
So what does this all mean? Let's trace the arc of this incredibly dense technical journey we've just taken. We started by entirely shattering the comforting illusion that minimal shapes equal a universal human language, learning from that localized agricultural app that a user's professional context fundamentally rewrites digital semiotics.
Which is a huge lesson.
We navigated the great label debate, utilizing Hick's law to understand that while a beautifully drawn icon might save physical pixels, a single, highly legible text label saves invaluable cognitive processing time. We literally stripped icons down to their architectural primitives, abandoning the pen tool to learn the Boolean magic of the 45-degree rotation hack, ensuring our vector paths remain mathematically pristine and free of aliased blurring.
So important.
We explored the deep psychological impact of style, realizing that thick strokes and rounded radii trigger evolutionary feelings of safety and approachability, while sharp, microscopic corners demand enterprise-level respect. We threw our flawless designs into the brutal scaling survival matrix, proving exactly why the physics of subpixel rendering and anti-aliasing will mercilessly obliterate complex outlined icons on small screens.
Right.
And finally, we mastered the ultimate optical illusion, learning to actively defy the software's mathematical grid, pushing circles, triangles, and irregular shapes past their bounding boxes to achieve a perfect optical equilibrium that the human eye inherently craves.
That's quite the journey.
Great UI design, as it turns out, is absolutely not just an aesthetic pursuit. It is this incredibly beautiful, phenomenally complex intersection of behavioral psychology, hard vector mathematics, physical screen technologies, and an almost extreme level of empathy for the human being desperately trying to navigate the digital world you've built for them.
Takes a lot of care.
It does. If this deep dive has sparked a realization in you and you understand that mastering these foundational invisible mechanics is exactly the advantage you need to elevate your design career, I cannot recommend the source text of today's breakdown highly enough. The book is titled Design User Interface.
It's a must-read.
It is an absolute goldmine and to make it as frictionless as possible for you right now, you can easily buy the book right now by scanning the QR code of the book link provided in the description below. Seriously. Pause the audio, pull up the description, scan that code, and get this architectural blueprint into your design toolkit.
Definitely do that.
And if you want to continue leveling up your technical skills with us, diving deep into the microscopic details that actually matter, please make sure to follow us for more technical design breakdowns and career-building content just like this. We absolutely love unpacking this architecture with you.
As we wrap up today's incredibly technical analysis, I want to leave you with one final structural paradigm shift to mull over. Everything we have meticulously deconstructed today, the bounding boxes, the anti-aliasing survival matrix, the optical weight of a 2D circle versus a 2D square, relies entirely on the physics of flat glass screens. The rigid, two-dimensional X and Y grid.
Yeah, that's what we have right now.
But as our technological environments rapidly transition toward the immersive, as we move definitively from the flat glass of smartphones into the volumetric z-axis of spatial computing, mixed reality, and augmented environments, what happens to this visual vocabulary?
Oh, it's a wild thought.
Will the highly abstracted, flat geometric icons we've analyzed today become obsolete, charming relics of a 2D past? Or will these simple, mathematically distilled geometric shapes prove to be such a permanent, hardwired component of human cognitive processing that they survive the leap into 3 dimensions? The next time you wake up, grab your phone and let your thumb hover over that tiny, mathematically imperfect little house icon. Ask yourself, what is this shape really trying to communicate to my brain?